Hello, welcome back to my video and welcome back to my channel. So this time we'll be talking a second video for our complex analysis series. So this is actually rectangular representation of complex numbers. So of course, when we think about this rectangular representation of these complex numbers, observe that like the real number x, that can be represented as a point in the line, we can do the same to complex number. Let's consider this. We have z equals xy. So in the context of complex plane, sorry, with my drawing, let me draw this again here. Okay, here. Okay, so if we have this as a real image or the real axis, and this is the imaginary axis. Sorry with my penmanship. So let's say you have a point here, x and y. So this is our z here. So this is actually a rectangular representation of the distance from the origin here to here. So this is a rectangular representation because this is our x here and this is our y here. Which means that this xy here, each point rather, so if you have each point xy on the complex plane, it actually determines a two-dimensional vector from the point 0, 0 to the point, which is the initial point here, to the point here, which is our terminal point. So this line, this here, so assuming I have a very perfect drawing, sorry. So this straight line here is a directed line segment. So remember that from our addition on the past video, we have the set of complex numbers is defined in the addition in this way. You just have to get the sum of the n3 y's. This is actually a geometric, we can actually provide this as a geometrical interpretation via parallelogram method. So this is actually the same with, because if you notice, this is actually a directed line segment from the point 0, 0 to the point xy. So that means it's actually a vector representation. Now, if you have this addition here, it's actually the same as doing the vector addition we have in physics. So let me show a representation for the vector addition here. So observe that suppose we have the the complex plane here. Okay, and let's say you have z1 here. You also have z2 here. So remember that what we do in physics when we do vector addition is that you have to create an image for z2 here and another image for z1. So assuming I have, okay, I think I just extend it so much. So somewhere this is just the point of intersection. So you just have to connect from the point of the origin of z1 and z2 connecting to this terminal point of the reflection of z1 and z2. So basically this is our sum, the z1 plus z2. That's it. So of course, in the context of a complex plane, we will have to consider some terminologies. First is, we have this. The magnitude of the center xy is the distance of the point z xy from the origin. Okay. The second is the distance is called the modulus. So the distance is called the modulus of the complex number z and is denoted by the symbol. And you have this equality. So technically, your magnitude is actually the length. Your modulus is actually an absolute value because it's actually a distance. So based on the fact that this is here, this is our z here. So this is a terminal point here. It's actually taking the distance from this terminal point from the initial point. So that's technically the same as getting the distance from a point to another point. So it's actually a modulus. So note that for every positive real number x, I'm sorry, real number r rather, there are infinitely many distinct values xy whose absolute value is r. So basically, you can just imagine that by taking the modulus of z, in which the modulus of z is r, it actually refers to infinitely many values of x. Because remember, you have to take the absolute value here. So that means this is equal to the square root of x squared plus y squared, right? And basically, either you can take, you can have x having a value, or you can have x to be equal to r, and y is 0, or you can have y to be equal to r and x is 0, and many other cases. So that means you can just make an infinitely number of many distinct values of x and y. And note that what we have discussed the last time on the video is that remember, for a complex number z, which is xy, the first ordinate is actually the real image of x, I mean z. This is actually the imaginary image of z. And so we can write z equals x plus iy, which means that the absolute value of x, because x and y here are real numbers, so the absolute value of a real number here is actually the same as the real image of z. Technically, this is less than or equal to the modulus of z. And the absolute value of y here is equal to the imaginary image of z. This is less than or equal to the modulus of z. So let's consider another definition here. So the conjugate. So given that you have a value z equals xy, so the conjugate, so denoted by the symbol, so there's a bar on top of z, is actually the point x negative y. So basically, this is a reflection of the directed line segment with respect to the x-axis. So say for example, you have z here equals xy. So you have complex plane here, x and y. And if you have z here, z here, its conjugate is actually the reflection with respect to the x-axis. So this is actually the z bar here. So whatever would be the angle of elevation with respect to the x-axis, this is actually the same as the angle of the depression with respect to x-axis. Okay? So let's consider the properties here. First property is this one, the sum of the complex number and its conjugate is actually the same as twice the real image of z. So how do we do that? Let's consider this proof here. Suppose you have z here equals xy. And of course, the conjugate of z is x negative y. So if you take the sum of z and its conjugate, so basically you have x and y plus x and negative y. So remember that the binary, the addition, which is a binary operation of the complex number, is defined in this way: x plus x, y plus negative y, and so you have 2x and 0 here. So this is actually 2 ray of z. That's it. Okay, another property is this. The sum of the complex number and the negative of its conjugate is this: 2i times the imaginary image of z. So you can do this in your way to show the proof of this. But if you have a question, you can comment down there on the video. But basically, the proof for this is very easy. Same with what we have done with the first property. Third property is the modulus of the number and the modulus of its conjugate are equal. And the product of a complex number and its conjugate is actually the square of the modulus of the complex number. So since we are on the level of interpretation, the rectangular interpretation of a complex number, so let's consider first an equation of a line in a complex plane as an interpretation here. So of course, we may write an equation of a straight line in the plane with real and imaginary axes as coordinates. So observe that equation of a line can be written in this way, right? Here, ax plus by, sorry, by plus c equals 0. Okay, and observe that you have using the properties, we have a z plus z bar. I have 2 re of z, and so I can have z plus z bar equals 2x, because x is the real image of z, given that your z is x plus iy or xy. Okay, and also I can write these as z plus z bar over, I'm sorry, my bad, over 2 equals x. So I have x equals z plus z bar over 2. And also I can solve for y as using the same property. I have 2i imaginary image of z equals z minus z bar. So I can have 2i y equals z minus z bar. Therefore, my y is the same as z minus z bar over 2i. So I can substitute these two equations here from this. So I have a times z plus z bar over 2 plus b z minus z bar over 2i plus c equals 0. And of course, at least one of a or B is not 0, so that we can still have the equation for a line. Okay? And if I'm gonna simplify this one here, I'm not gonna do it by how did I do it with algebra, because we're not talking basic algebra here. But you can simplify it this way. You can verify that this is A minus IB equals Z plus, sorry, A plus IB Z bar plus C plus 2C rather. So if I assume that, let's say, if I'm gonna assume that this is an alpha, this is a beta, and 2C here is a gamma. So basically, alpha is the same as the conjugate of beta. Then I can write this equation as alpha Z plus beta Z bar plus gamma equals 0. So this is now the equation of a line in a complex plane. Okay, so if you have question or clarification, you can comment down there on the video. So let's go to the second one, the equation of a circle in a complex plane. So remember that the definition of a circle, so let me write the definition of the circle, although I have made a point here, an emphasis on my video for a circle before, so you can check down there. The equation of a circle is a set of points equidistant to a fixed point called the center. So such distance is actually called a radius. So remember that the standard equation of a circle is x minus a squared plus y minus b squared equals r squared. So your r, of course, here is greater than 0 because we're talking about the distance. So it's actually a radius. Now, suppose that z is equal to x plus iy, and your z sub 0 is a plus ib. Then, if you subtract these, I would have x minus a plus y minus b, right? And so if I take the product here, I would have z minus z sub 0 and z minus z sub 0. So remember, using the property, I would just get the square of the modulus of z minus z sub 0. And so I would get x minus a squared plus, sorry, I think I have a very bad penmanship here. Sorry, I'm just trying to be okay with this new drawing tablet here. Okay, hang on. Okay, so here, y minus b quantity squared equals r squared. So in this case, this z sub 0, so we have, this is now the equation of a circle in the complex form with center z sub 0. So this is now your center z sub 0, and you have the radius as r. Okay, so technically your equation is z minus z sub 0 equals r. Okay, to further simplify on these, we can have this equation as this one. Where can I write somewhere here? Okay, here. Let me erase this. Okay. Observe that I can write z bar equals, sorry, shouldn't be equal, sorry, my bad. Okay, it's just minus, so z minus z bar minus z sub 0 bar plus z 0 bar plus z sub 0 z sub 0 bar equals r squared. Okay, and basically I can write this as z sub 0. I'm sorry, it's z bar minus, this is actually to the real image of z times a minus ib, right? Because a minus ib, oh, I'm sorry, it's a plus ib because this is actually the z sub 0 originally, plus a squared plus b squared minus r squared equals 0. So therefore, I can write this as alpha. The product of these is actually the same as this. And I would have beta z plus beta bar z bar plus gamma equals 0. So that's it. But it's just only for simplicity. But I would suggest this is just the only equation of a circle here. Okay, so one last example is this. We will use the triangle inequality to find the upper bound and the lower bound of the inverse of the absolute value, or the modulo of z4 minus 3z plus 1, whenever the modulo of z is equal to 2. Okay, the goal here is this. We must find, so our goal here is we need to find m and capital M such that I have m less than or equal to z to the 4 minus 3z plus 1 to the negative 1 less than or equal to m, because we're actually looking for the lower bound and the upper bound. Of course, for z, for the modulo of z equals 2. Okay, now observe that, okay, so let's do the solution here. So observe that z to the 4 minus 3z plus 1 should always greater than or equal to, if I'm gonna separate z to the 4 minus this. Okay, this is actually triangle inequality because this is always greater than if we are going to separate this and you have minus in between. So if the modulo of z is equal to 2, so I'm pretty sure this is 2 to the 4 minus 7 equals 9. Why? Why is that so? Observe that your 3, okay, so let me make an explanation here. Here, 3z minus 1, I can write this as less than or equal to 3z plus 1. Of course, it's greater because they're actually taking the minus here, but I'm taking the plus here. So it's always greater. Now, my z again is equal to 2, so I can write 3 times 2 plus 1, so I have 7. So basically, 7 is always greater than this, right? So if I'm going to subtract 7 here, so this is always, this thing here is always less than this, and this is less than this. So therefore, this is actually greater or equal than this. Okay? Now also, z squared, z to the 4 rather, minus 3z plus 1. This is always less than or equal to z to the 4 plus 3. I'm sorry, so it's modulo of 3z minus 1. And this is actually equal to 2 to the 4 plus 7 equals 23. So we're pretty sure that this modulo here is less than 23. But observe that we're just taking the inverse here. So therefore, I would have 1 over 23 less than or equal to the inverse because you're actually taking the inverse here. So the A inequality will be changed. So this is now, so, okay, sorry. Okay, so therefore this is now the lower bound, this is now the upper bound. That's it. So guys, if you have question, you can comment down there on the comment section of the video. So for those who are new to the video, you may subscribe to my channel so that you will be updated for the videos that I will be uploading. So I'm not just talking about the complex analysis, I'm also talking to the different types, different areas in mathematics. You can comment down there for your request on what subject will I be dealing here. So as much as I can, I will be more than glad to provide you a video. So thank you so much, guys, for listening. And once again, my name is Mark, and please comment down there for any questions and clarifications. Have a great day to you.